let's get started. Our last section, and we are going to be doing antiderivatives today and probably finishing it off tomorrow. Antiderivatives is a process. So let me show you what it looks like. Suppose I take a function f of x, let's call it 4x cubed, take away 6x squared, plus 10x minus 1. And I differentiated it. Well, I do the power rule, multiply by the power, reduce it by 1, multiply the power, you get 10, and that number would just disappear because the derivative of a number is 0. Now, when you go from this function to that function, and we call that process differentiation. Imagine I gave you the derivative of a function. So I told you what that was. And your job was to find out what the original function was. And when you go that way around, this process is called antiderivative. It's also got another name, it's also called integrate. And that's what we're going to be focusing on today and tomorrow. How to take a derivative and essentially find the original function. Now we know the answer. It's 4x cubed, take away 6x squared plus 10x. Now, pretend you didn't know that -1 was there. Couldn't this be plus 5, plus 42, or minus 1,000,000? Couldn't that number here be any number at all? Because there's no way of telling what that number would have been, right? And because of that, we have to write down this guy here, plus capital C. And that's called the arbitrary constant. So when you do the antiderivative process, you don't know everything. You'll know all the things have x's in it, but there'll be this little, well, we can never know what the number was because any number that was here gets destroyed when you find its derivative, right? And if all you tell me is the derivative, I don't know what that number was, right? The information is gone. So that's the process we're going to be doing. And, well, let's start off. I'm going to give you a list of functions, and I'm going to put the derivative here, and next to it, I'm going to put what the original function that has that derivative would be. So I'm going to do. Okay, if the derivative was 6x cubed, then the antiderivative is this. If you differentiate this, you will get 6x cubed. So I'm going to put down a new one now. Six x cubed gets you 3/2 x to the 4. 4x gets you 2x squared. The antiderivative of -10x to the 4 is negative 2x to the 5. They all have a plus C on it. Anybody want to have a shot using patterns what this guy would be? What is the antiderivative of ax to the 4?
8/5 x to the 5th.
Okay, agreed. At least one of you know the pattern. Anybody want to have a shot at this one?
2/5 x to the 5th minus 3x to the 4th plus 3x squared.
Okay, Cara, tell us what you're doing.
Adding 1 to the power, then dividing by the power.
Yep. So this is going to be our first group of functions that we can find the antiderivative of. And there's a name for that rule that you just described to us. It's called the power rule for integration. And I just want you to remember integration is just another name for antiderivative. So what does the power rule say? The power rule says, if you know that the derivative is ax to the n, right? 5x cubed, 7x to the 10, anything that looks like that, then the original function will be add 1 to the power and divide by the new power. And then always remember to put that arbitrary plus C at the end. And that is called the power rule. So let's use the power rule. Suppose I tell you that the derivative is equal to 3x to the 5, take away 2x to the 4, plus 7x. Then the original function, the power rule, add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power. Add 1 to the power and divide by the new power, plus C. And you should be doing any simplification as it happens. So I kind of forgot to do it with that one. And if I want to check, have I done this correctly? Wouldn't I just differentiate this function? And shouldn't I get that guy if it works? Well, you know that there's a power rule for differentiation, isn't there? Right? Multiply by power reduced by 1 works. 10/5 gets me 2 works. That guy gets me x to 7. All of this works. Right, if I want to find the antiderivative of 3x add 7, and I use the power rule, this guy is basically x to the 1. So when you add 1 to its power, you get 2, and you divide by that new power, you get 3/2. What is the antiderivative of the number 7?
7x.
You nailed it. And isn't 3x and 22 is going to be 22x? So when you find the antiderivative of a number, don't you just get the same number with an x? And if you think about it, it kind of makes sense. What do you get if you differentiate 7x? You get 7. What's the antiderivative of 7? 7x. So far, so good. We've got this new guy in town called Antiderivatives. By the way, that's what Calc 2 spends most of its time doing, working with and finding antiderivatives. We tend to call them integrals. So let's talk a little bit about notation. There are two main ways in which you are asked to find an antiderivative. The first way is they'll tell you what the derivative is, and they'll ask you to find f of x. And the other way that they do it is they tell you that there's a function called f of x, oops, and they'll ask you to find capital F of x. Both these are really telling you to do the same thing. They're telling you to find the antiderivative of this guy. Now notice how one of them works. They tell you the derivative and they ask you to find the original function. In the other case, they say, look, here is a function, find the thing that's called the antiderivative. How do we note the antiderivative? The notation is you use the same letter, but a capital. So if this was little g, they would say find big G of x, right? If this was little h of s, they would say find big F of x. Now, suppose I gave you a question like this. G of t equals 21 t squared. And I said to you, find capital G of t. Do you now realize that they're saying find the antiderivative? Right, there isn't any, there isn't really much in the way of English here. The grade is just a function and find this guy. So capital G of it, capital G of t is a power rule. Add 1 to the power and divide by the new power. Remember to put your plus c at the end. Are you comfortable with the two types of notation? Right. They tell you a function called f dashed of x and they say find f of x. That process of solving that problem is essentially finding the antiderivative of this polynomial. Or they might say, here is a function, find capital F of x, which is exactly the same as this one, right? The only difference here is that here the answer would be 2/5 x to the 5, take away 4x squared plus 7, I'd say. And in this case, capital F of x would equal 2/5 x to the 5, take away 4x squared plus 7x, I'd say. Any questions? Are you comfortable that if I gave you a polynomial, right, things that look like this, that you'd feel sure that you knew how to find its antiderivative? Yeah, let's try it. Try it. Give you 3 questions. Okay, there they go. You got 90 seconds from now. Okay, let's go for it. Power rule every single time. Add 1 to the power, you get that. Divide by 6 gets your third. Add 1 to the power, you get that. Divide by 2 gets your half. 1 gets you 1x, and you finish with your plus arbitrary constant c. Antiderivative, capital G of x. Add 1 to the power and divide by the new power. -1 gets you -1x plus an arbitrary c. Okay, last one. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. We've got it. So hopefully you were getting the same answers, right? We call this process that we've just done finding antiderivatives. And I'm going to have a little table here as we add things to our list. And I'm going to use the capital notation. Right. So the first one is the power rule. And the answer is, the power rule says, add 1 to the power, divide by the new power. Okay. Here's our next function. Any volunteers? What is the antiderivative of e to the x? So you're thinking, what function do you need to start with that if you differentiate it, you end up with e to the x?
E to the x.
E to the x. I love e to the x. It's such a nice, well-behaved function, isn't it?
Couldn't it also be negative even? Oh, never mind. I was gonna say
You've
negative
answered
e
your
to
own
negative
question,
x.
right? So in my little list, I'm going to now put e to the x, and its antiderivative is e to the x plus c. So suppose I have a function called g of t, and it's 3e to the t plus 5. And I want to find its antiderivative, so I'll ask you to get g of t. Well, if the antiderivative of e to the x is e to the x, isn't 3 of them just 3 of them? And we know how to do numbers, and we always finish with the c. And how about negative e to the x? What would the antiderivative be? Negative e to the x, what's the antiderivative of it? Can't have you stumped, come on. What function would you have to have here that if you differentiated, that's the guy you would get as the answer?
Negative e to the x.
Yeah. Isn't e to the x just well behaved? Not really anything else I can add to that, would you agree? I mean, that's about the most I can do right now to e to the x, right? Double it, stick a -1 in front of it. You're pretty much done. So let's look at trig functions. So we're going to look at how do you find antiderivative of trig functions. Now, you might have thought that if we were going to do antiderivative of trig functions, I would be writing down all 6 trig ratios: sine x, cosine x, tan x, secant x, cosecant x, and finally cotangent x. You would think that, wouldn't you? But I didn't, because at least half of those trig functions that I mentioned, their antiderivatives are not obvious and are not easy. So the ones I've got here are the ones you are expected to know. And 2 of them are straightforward and 2 of them are a little bit weird, but we'll come to that in a minute. Be careful here. What is the antiderivative of sine x?
Negative cosine.
You got it. Why did you need that negative?
Because when you differentiate cosine, you get negative sign.
You see that, guys?
2 negatives.
Yep. One of the most common mistakes that people make when they do antiderivatives with trig functions is that they get the sign wrong. In other words, they think it's a plus when it should be a minus, or vice versa. On the other hand, then, what is the antiderivative of cosine x going to be? What
Sin
function?
x.
Sin x. Right, we get 2 weird ones here. A guy called secant squared. There's a function over here that if you differentiate it, you get secant squared. So that function that's over here, I hear tan x. Do you agree? Tan x is the guy that works. Secant tan. A little bit less common, but it is an answer. That, you know, it's a doable answer. What function goes here? Right? What thing do you differentiate to get this?
Secant x.
You get secant x. So over in my little list, I'm now going to put sine x is the negative of cosine x. Cosine x is a positive sine x. Secant squared x is tan x. And secant x, tan x, it has an antiderivative of secant x. So let's put that together. Suppose I have a function f of t, and it's 3 sine t plus 4 cosine t. Take away secant squared x plus 5. That's just a random combination. And you're being asked to find its antiderivative, f of t. Well, you'd say, okay, if you find the antiderivative of 3 sine, you get negative 3 cosines. 4 cosines gets you positive 4 sines. A negative secant squared gets you a negative tan. Put in the 5 there just because I wanted to, and finish with a plus c. So as long as you know what the antiderivative of the pieces are, can't you get the antiderivative of any plus minus multiple combination of it, right? If you want 5 cosines, just stick a 5 there, right? You want negative 2 of these, stick a negative 2 there, right? Constants follow each other. Any questions so far? I want to find the antiderivative of that guy. So we have to figure out how we're going to approach this question.
Could you start by making x a negative 1?
It's a good start. It's not going to work, but it's exactly what you should do if you were approaching a question you've never seen before. You'd write it in a format that gives you an idea. Now, shouldn't I be able to use the power rule? Well, what does the power rule say? You add 1 to the power, and then you divide by the new power. You see we're in trouble. This guy is a special case. There is a function that you already know, whose derivative is 1 over x. Scan through your brain. What function has a derivative that is 1 over x?
Vanessa said it in the chat, but natural log.
Thank you. You all agree? Differentiate and natural log. So that is a very special case. The power rule does not work with 1 over x. 1 over x has an antiderivative of log x. Well, how about 10 over x squared? Do we have to keep doing special cases every time that happens? No. And just like someone said, let's rewrite it as x to the negative 2. And this time, we'll try the power rule and see if it works out. Add 1 to the power. Divide by the new power. Make it look pretty. Oh. Isn't 10 over x squared okay? Can't you use the power rule on 10 over x squared? Right? You can just call it that, add 1 to the power, and divide by the new power. Everything works great. So I'm not going to have a new rule for fractions. Doesn't that rule cover 10 over x squareds? I don't need to rewrite a new rule. It's part of the power rule, right? Add 1 to the power, divide by new power. I want to find the antiderivative of a square root then, like 4 square root of x's. First thing I'm going to do is rewrite it as a fractional power, which is what I would be doing if I was trying to differentiate. Wouldn't it be nice if the power rule for antiderivatives would work on fractional powers? We know it works on negative powers. We know it works on these guys. Will it work with fractions? And the good news is it works with fractions. It's a little bit messier because fractions are messier by their very nature. You add 1 to the power. Now, you then divide by that new power. Dividing by 3/2 is really awkward, isn't it? So instead of dividing by 3/2, what I'll do instead is multiply by its reciprocal. Right? Instead of dividing by 3/2, I'll multiply by 2/3. And that ends up getting me this answer. And that actually works. You could check it out and differentiate it. Of course, we still have the style point rule. And the style point rule is make it look like the original. So that's the final answer. So when we're talking about style points in antiderivative questions, we're really mostly talking about make it look like the original, right? You're not really going to do factoring because that plus C kind of kills the factoring thing, unless you felt like it. And the one about trig, well, if it's trig, there might be some trig identities you can use. That's still in place. But most of the time, it's going to be make it look like the original. So let's try another one. Suppose I had 6 cube roots of x. Right, I want to find its antiderivative. I will rewrite it as a fractional power. Now I can do the power rule. Add 1 to that and you get 4/3. Dividing by 4/3 is the same as multiplying by 3/4. That guy times that guy, 2 there, that's 3, 9/2. Make it look like the original, and don't forget your plus C at the end. Are you comfortable that the power rule can be used for square roots and cube roots? Cube roots, square roots. So this power rule is pretty versatile, right? You can use it for 5x cubes. You can use it for 4/x cubes. You can use it for the cube root of x, right? You can use it for all 3 situations. The only guy you have to be a little bit aware of is the special case, right? 1/x. Quick pause. Any questions? If we feel good? We feel okay then. If we don't feel good, feel if I gave you a function, you'd be able to do it. Okay. There are not too many more things to add to our little list today. Let's take a side issue. Let's go back to differentiation for a minute. What is the derivative of 3 to the power of x? It is 3 to the power of x, but there's an extra bit added on, isn't there?
ln of 3.
Are we comfortable with that? Can you remember that guy? Now, what do you think you do when you find the antiderivative of this guy? It's still going to be 3 to the x. What about the log 3 guy? Where do you think it
Divide
goes?
by it.
So here is a new guy to add to our list. If you want to find the antiderivative of, well, I shouldn't really call it 3 because it could be any number, a, right? A to the power of n. Then its antiderivative is a to the power of n divided by the natural log of a. So try that one. Suppose I was wanting to find 4 times 7 to the power of t. Put little brackets to emphasize it so it doesn't look like 47. Plus e to the t minus a t plus a 1. Well, each piece gets dealt with using its own rules. That guy is still e to the t. This guy is a power rule. Add 1 to the power, divide by the new power. The number 1 gets me a t, and we always finish with plus c. I've got this guy. It's going to be 4 times 7 to the power of t all over the natural log of 7. And there, oops, a bit wobbly, but there is our antiderivative. Okay, let's look at homework on WebAssign. So this is a kind of, oh, got Windows in top of Windows. Go away, window. Don't want you. Try that again. There. Are you looking at question 1, for instance? Right. Now, there's a lot of questions, as you can see up here. There's over 20, is it 30? 25. So there are 25 questions, but at least half of them are like 10-second questions, right? If you know what to do, the answer's done. Right, so antiderivative of 7 would simply be 7x plus your RBTC. And I believe that WebAssign is very touchy. Will you make sure it's a capital C and not a little c? I've got a recollection that somebody last time said, nah, it didn't like little c, right? Okay, so it likes capital C. Isn't this question a power rule? So I'd add 1 to the power, which is 3, divide that by 3, and you get 7. So the answer would be 7 t cubed, oops, t cubed plus c, oops, plus c. And so, oh, come on, how many buttons can this darn thing have? There. My caps lock is not going away the way it should have. And there we go, finally fixed it. Actually, I should just use that button over there if I was trying to be too clever. Okay, let's just basic recap. I'll take a volunteer. What is the antiderivative of sine q? You got 50.
Cosine
Oh, you nailed it.
plus c.
I don't know why it's got extra brackets. I should watch, but I'm not, as you can see, a good one. I'll not write this one down, but I'll take a volunteer. Antiderivative of 6 e to the x.
6 dx.
We'll see. What's the antiderivative of 6 over t? You remember that's a special case. 6 over t. No takers? 6 over t?
6 on t.
Oh, there I go with my capitals back to front. There we go. I wish WebAssign would stop predicting what it thinks I meant. Okay, secant squared. That's basically a straightforward memory one.
10.
Tan. Now, if they give you a function like this, don't you just combine the rules that we talked about? So that would be a power rule, wouldn't it? So 3x squared plus 5x plus c, that would be a power rule. Okay. Don't need the answer to question 6, but what should you do first before you even try and find antiderivatives?
Expand it.
Right, so distribute the x. And in question 7, shouldn't you FOIL it out? Now, that guy is totally ugly. Not arguing with it, it is totally ugly. But isn't it just a power rule, nonetheless? You just have to be more careful because there are a lot of fractions going on. So I think I'll do this one. I'm going to add 1 to that. Won't that get me positive a third? Great. So x to the power of, there I go in capitals again, x to the power of 1/3. And it liked fractions, it's not my fault. So that's add 1 to the power part did. Shouldn't you then divide by the new power? Well, dividing by 1/3, isn't that the same as multiplying by 3/1? So that's why this guy here is 15. I want to try something here. Yay, it looks much nicer without those brackets around the third, doesn't it? Okay, that's the first one done. Now, if you add 1 to 5/3, you'll get 8/3. So I'm adding 1 to the power, 8/3. I'm now going to divide, right, this guy here, by 8/3, which means I'm going to multiply it by 3/8, which gets me 6/8, which gets me 3/4. And we're done. If you were going to do question 9, wouldn't you just turn that into x to 1/2 and the cube root into x to the 1/3, and then it looked like this question we just did. And for the last question for today, let's look at question 10. And it bears a lot of resemblance to things when we had to differentiate. So if you think back to when we were beginning with differentiation, that we had to differentiate a function that looked something like this. And we know we can't differentiate it when it looks like that. At least you couldn't when we started doing these. I can't find antiderivatives of this either in the form it's in. So I have to rewrite it. And I have to rewrite it in such a way that I can use a power rule. Any suggestions how to take on this challenge?
What if you move the t to the 1/2 to make it a negative t to the 1/2 and then distributed it?
And
That
while I'm
right?
at it, I'll make that square root of 1/2 as well. Are you comfortable what happened there, that t, square root of t became t to 1/2, and then I'm moving it up here? And this square root of t became also t to 1/2. Now, if you distribute this, 2t times t to the -1/2 gets you that guy. This guy times this guy gets you -4 t to the -1/2. And this guy times this guy gets you something quite interesting. What do you get if you multiply 5t to the +1/2 by t to the -1/2?
5.
You just get a 5. T to the 0 is 1, so you get 5. Now, I haven't answered the question right. All we've done right now is turn the original question into a format that's going to allow the power rule. Now we can do the power rule. Add 1 to the power. And divide by new power means multiply by 2/3, so you get 4/3. Add 1 to the power, you get a 1/2. Divide by a 1/2 is the same as multiplying by 2. 5 gets you 5t, and then add c. And finish with your style points. And your style points are, make it look like the original. And we are done. So last name, bye-bye, and we'll finish these guys off tomorrow. And of course, I'll hang about for any questions.